In this lesson, let's discuss about reinforced concrete design principles. When the section has been loaded, the beam undergoes deformation. The top layer of the beam subjected to the compression and bottom layer of the beam subjected to the tension. Whereas concrete is weak in compression and strong in tension. So that's the reason we introduce the reinforcement in the tensile zone to take care of the tension, and in the compression zone, concrete will take care of the strength effectively. So since we are introducing the reinforcement in the concrete zone, we call the entire cross section or entire the beam is a reinforced concrete beam. So whereas come to the design methods used in the concrete based on the cross section classifications, how it has been classified as under reinforced section, balanced section, over reinforced section. The way we have explained very beginning, the compression force and tensile force. This is the strain in the concrete, strain in the steel. So either you can differentiate this based on the stress, strain, or based on the neutral axis. Neutral axis is the one which differentiates the tensile zone and the compression zone. So now come back to the under reinforced section. The name itself is indicates under reinforced. The reinforcement is less than the balanced section, which is called under reinforced section. Similarly, the balanced section, also the name indicates very clearly it has been balanced, means that the force in the compression zone and the force in the tensile zone equally carries the external loads. So over reinforced section, sometimes due to the depth of the section limitation, over reinforced sections has been designed, but they have some disadvantages. We'll discuss on that. So over reinforced sections, the neutral axis which is greater than the actual neutral axis. So neutral axis also one of the criteria to define this under reinforced, balanced and over reinforced, how it will be. If you look into the balanced section, the XU limited, which also called as a limited neutral axis, critical neutral axis or balanced neutral axis. There are many ways we can call that one as a XU limited. This limited neutral axis or critical neutral axis, which is equal to actual neutral axis, which is called as a balanced section in terms of neutral axis. Whereas in under reinforced section, the neutral axis, actual neutral axis, which is less than the critical neutral axis, which is in the green line, called as a critical, the under reinforced section. So now come to the strain theory. So when there is a under reinforced sections has been used, the name itself is under reinforced. Reinforcement is lower than the balanced section. Obviously, when the section has been loaded, since the reinforcement is low, the strain reaches first in the tension zone, which is the reinforcement. Later, the compression will reaches its maximum strain, which is normally 0.0035 in the later stage. So that means we'll discuss the crack theory in the next slide. So now come to the balanced section. Both concrete and steel reaches simultaneously the strain, maximum strain. Whereas in over reinforced section, the concrete reaches the maximum strain at first and then the steel. Based on this also we can able to classify the under reinforced, balanced and over reinforced sections based on the strain theory. Now come to the stress strain for concrete and steel. So we all know concrete is a brittle material and steel is ductile material. So based on the theoretical investigation, I superimposed concrete curve and the strain curve. So how it works in reality for the failure scenarios, whereas in concrete, if it reaches the yield point, and if you look into the failure, it's very short distance, the duration is very less, the deformation is very less. So that means once it reaches the yield point, any further load increased, sudden failure may occur. So that's called as a concrete brittle failure. Whereas in the yield point for the mild steel, for example, this is the yield point and this is the failure point. You have enough deformation before it goes to the fail. So steel is the ductile material. It has providing the enough deformation before it fails from the yield point. So that's why we have enough time to understand the failure mechanism when the steel is actually in the critical scenario. And if you look into the tensile strength of the concrete, which is 0.7 FCK, and for example, if you take M25 concrete, 3.5 Newton per mm square or MPa. But whereas in tensile strength of the steel, even for the mild steel, which is 250 MPa, so very much higher than the concrete tensile strength. So that's the reason we always say that concrete weak in tension. It won't take much load, tensile load. So now if you look into this failure mechanism, and next if we go to the section classifications, now under reinforced sections. So think about here, the steel reaches first and the concrete reaches strain in the later stage. And this XU and XU limited will be calculated based on the strain theory. The limited or balanced neutral axis equal to D means depth, effective depth of the section, 0.0035 by 0.0035 plus epsilon ST. So this gives us the limiting neutral axis depth. And then actual neutral axis depth based on the reinforcement, 0.87 FY AST by 0.36 FCK B. This gives us the actual neutral axis. Now, if the actual neutral axis, which is less than XU limited, straight away we can assume that this section is under reinforced section. And as stated in the earlier, since under reinforced section, steel is the first and then the concrete. So that means steel first reaches its maximum limit. That is good for us, because if it reaches any further load increase, it has an enough time or enough duration or enough elongation before it fails. Right? So it gives a clear indication before it fails the entire section. So that's the reason we prefer to design the section as under reinforced section compared to other cross-sectional criteria. So in this case, of course, it is a ductile failure because steel fails fast, and it will be giving an indication for failure. And we have enough safe time before the failure occurs. And now come back to the balance section. So balance section, since both has been reaching the ultimate strain simultaneously, there is a chance that concrete also may fail and steel also fail at the same time. But however, compared to the over reinforced section, balance sections are better. This also sudden failure may occur due to the concrete brittleness. Now come back to the over reinforced section. Whereas in over reinforced sections, the strain in concrete reaches first and then steel reaches in second. So now if you look into the failure mechanism, one step up in the graph, first concrete reaches failure, the yield strain first. That means there is not much enough deformation before it goes to the failure. So that's why the over reinforced sections, if it fails, if it takes the extra loads more than what we have designed, it may happen that sudden failure will occur without any notice. So that's why most of the cases we don't opt for over reinforced section. Rather than in these kind of scenarios, normally when we go to the over reinforced, because the depth is restricted, we cannot increase the depth of the section. In that condition, over reinforced sections has been designed. But however, to avoid this sudden failure, we may opt for doubly reinforced sections. So we may opt for doubly reinforced sections. So in that situations, what will happen? The tensile zone reinforcement, some portion will be designed for compression steel as well. So that's why we can skip this over reinforced cross sections. For a doubly reinforced section design, we'll discuss in the next chapter. Thank you.